I'm going to do a walkthrough of this paper that you had in February, March time as your mock. So we're going to start with the first question. So with this first question, we've got pentan-2-ol and pentene. So pentan-2-ol has the alcohol functional group, and pentene has a C double bond C. It's talking about boiling points, and we can see the boiling point of the alcohol is much higher than that of pentene. So immediately I would think of this as the intermolecular forces of attraction, and they're greater in the alcohol than in the alkene. Okay, so now it wants you to explain why that is the case. So we'd need to mention that the intermolecular forces in pentan-2-ol are much greater than the intermolecular forces in pentan-1-ene. We also know that in the alcohol, we've got hydrogen bonding. So we can talk about the hydrogen bonding being much stronger in the pentan-2-ol than the van der Waals forces in pentan-1-ene. And this is a 3-mark question. So those 3 points would get you the mark. So I've written my answer here, and I've said that pentan-2-ol has stronger intermolecular forces of attraction than pent-1-ene because the boiling point is higher. I've then said that pentan-2-ol has hydrogen bonding between the alcohol functional groups, which is stronger, which I've mentioned here, and that pentan-1-ene has weaker van der Waals forces between the molecules. So there are our 1, 2, 3 points for this 3-mark question. Okay, so let's have a look at part 2 of this question. Pentan-1-ene is formed by elimination of water from pentan-2-ol. State the reagent and condition for this reaction and outline the mechanism. So basically, you really do need to know this. So what we can say here, if we're eliminating water from pentan-2-ol, it must be some sort of dehydration reaction. And good dehydrating reagents tend to be concentrated acids, in particular concentrated sulfuric acid and concentrated phosphoric acid. So my acid of preference is concentrated sulfuric acid. So I'm going to write that down, concentrated sulfuric acid, and you have to say concentrated. If you don't say concentrated, you don't get the marks. And the conditions for these, it does have to be hot. It works very, very slowly in cold conditions. So the conditions are hot. You may want to put a temperature range. You could say high temperature. The temperature would range, if you put one, was 150 to 200 degrees C, but hot would get you the mark. And then you have to draw the mechanism. Okay, so when it says outline of a mechanism, it actually wants you to draw the mechanism, not describe it, not anything other than draw it. So here I've drawn out pentan-2-ol. We've got concentrated sulfuric acid, so I must have got hydrogen ions around. Okay, so the lone pair on the OH, the alcohol function, that will donate its electrons to the hydrogen ion, and we will create this intermediate here where we have a positive charge on that oxygen. So we've donated this electron pair, we've made a dative bond, and there's the dative bond, and there's the positive charge on the water. Now, on the alcohol. What happens next is the electrons between the carbon and hydrogen, that bond is broken, and those electrons are given to the oxygen. So we're going to eliminate water. So we eliminate water from this, and what we form is this intermediate here with a positive charge, and that's the water that has come off. Okay, I've drawn this a little bit badly because I could really do with making this like this. There we go. So I've got my 3 hydrogens there. What's going to happen next is the electrons between the carbon and hydrogen here are donated to this bond between the carbon and carbon here. So we're creating a double bond, and we'll create CH3, CH2, CH2, C, double bond C. I've only got 1 hydrogen on here, so that's the 1 hydrogen, and I've now only got 2 hydrogens on here. There's the 2 hydrogens, so that's the alkene. Okay, so I have made pent-1ene, which is what it was asking for here via this mechanism. Mark-wise, you've got 1 mark for this correct arrow, 1 mark for the correct intermediate, and 1 mark for this electron, pair of electrons being lost. So that's 1, 2, 3. And then you've got this carbocation intermediate where we then lose this electron here. So there's a mark for the intermediate and the loss of this electron, this carbon, this hydrogen here. So we create that double bond, and I've forgotten to put in that we then made, because we've lost this electron here, we've created this hydrogen ion. There's the hydrogen ion, and there's our final product. So we have our hydrogen ion here to start with, our hydrogen ion there at the end, and we can see that this is a catalytic process. Okay, I just hope I've put that better in focus. All right, let's have a look at 2.1 now. So 2.1 is a big question, 6-mark question. So we really need to break this down. Let's have a look. Explain the differences between structural isomers and stereoisomers. Use examples to show how compounds with the molecular formula C4H8 exhibit stereoisomerism and the 3 types of structural isomerism. Okay, so it's nice and easy to look at how to break this question down. So we're going to break it down into structural isomers and stereoisomers. And we know we've got 3 types of structural isomer. So if I was answering this question, I'd probably look at the structural isomer here. So I would plan it out, structural isomerism here, and then a little bit further down the page, somewhere down here, I'd probably write stereoisomerism. Okay. I know I've got 3 structural isomerisms, so I just need to make sure I mention them all. I've got chain isomerism, I've got functional group isomerism, and I've got positional isomerism. Stereoisomers, the only one that I know at this present time, well, I actually know a few actually. I've got EZ isomers, but I've also got optical isomers as well. Okay, oops, you can't see that very well. Let me just bring that down. So looking at structural isomerism, if I was to say I'd get 3 marks for this and 3 marks for this, that would give me 6 marks. If I can give examples of chain, functional and positional isomerism, that's got to be a mark for each one. And then with stereoisomerism, EZ, that must be a mark for that. Optical isomers must be a mark for that, and there must be a mark for stating something else. So I guess the other marks would be for giving the definitions of structural isomerism and stereoisomerism. Okay, so what I've done, I've put the definition for both of these down. So structural isomerism, molecules with the same molecular formula but a different structural or displayed formula. And stereoisomerism, molecules with the same molecular and structural formula, but a different arrangement of atoms in space. Okay, so the way I'm going to tackle this, I'm going to take a base molecule. So with C4H8, so C4H8, this could be butanene, so as butanene. Okay, so CH2 double bond CH, CH2 CH3. That's how I'm going to take it, and I'm going to write it like this. So using that as butanene. Right, I'm going to split this into the 3 different isomers and show how they are different to this as my base compound here. Okay, so I've put the 3 headings: chain isomer, functional group isomer, and positional isomer. So what I can do here is say that I will draw the positional isomer. So CH double bond CH, right, CH. What I'm going to do is I'm going to take this CH3 off here and I'm going to put it on this point here. So I'm going to make it CH3 and this would be CH3. So that's a positional, a chain isomer of our butanene. And so this would be 1, 2, 3, 1, 2. So this would be 2-methyl propene. And it's always a good idea to name your isomers. Okay, the functional group isomer of this would be where the double bond is no longer there, but we have this in a cyclo position. Okay, so cycloalkanes are functional group isomers of alkenes. So this is cyclobutene. Okay, and positional isomer. So positional isomer is where this functional group is in a different position. So I'm going to move that functional group and I'm going to move it onto position 2. So I'm going to put it in between carbons 2 and 3. And that will be my positional isomer. And I'll put that there and that there. Okay, and this is but2ene. Now I'm going to talk about, because but2ene can also be a stereoisomer because we can get E and Z forms of this. So I'm just going to put EZ but2ene and then I'm going to talk about it more here. Okay, so I've added here that with the alkenes, they have a restricted rotation around the C double bond C. So we get 2 forms, which are E and Z. And now I'm going to go on and draw the E and Z isomers. So I'm going to take this but2ene that I had before. I'm going to put 1 hydrogen up there and a CH3 down here. I'm going to put another hydrogen up there and a CH3 down here. I'm going to draw it again and I'm going to draw the other isomer. So there's the CH3, this will be the H and that will be CH3. Now I have to name them properly. So these are the 2 priority groups. They're on the same side, same side. So this must be the Z isomer. So that's Z but2ene, and these are on opposite sides, so this is E but2ene. Okay, now I did mention about optical isomers. We do have another isomerism here, stereoisomer here, optical isomers, but with this C4H8, this alkene, we can't actually get optical isomers. So it's not possible to form those optical isomers with this particular compound because we don't have a chiral center. We're not able to get a chiral center. Fortunately, then we won't be able to talk about the optical isomers with this. So this is where we finish our question. Okay, so going back through, we've got 3 types of isomerism. So I've given the definition. I've started out with C4H8 as, maybe I'll say, using C4H8 as butane for comparison. That would help. That would help the examiner know end comparison. So I've drawn it. That's butanene. And then here I've got my chain isomer, which is 2-methylpropene. I've got the functional group isomer, which is the cyclobutene. I've got the positional isomer, which is EZ-butene. So it's gone, the double bond's gone from the 1 position to the 2 position. I've then talked about stereoisomerism, so I've given the definition. I've said that alkenes have a restricted rotation around the C double bond C, and I've got 2 forms, which leads to, I'll probably put here, lead to 2 forms, which are E and Z. And then here are my E and Z. So this is Z-butene and this is E-butene. And I believe that hits all of those points required. But you can see how I've planned the essay. I've split it into 2 parts. I'm using C4H8 and I've got the 3 different structural isomers. It did say there were 3 and I've identified them here. And the stereoisomers, I've identified the 2 that I know, but I only need to use EZ. Okay, so this next question is talking about 2-bromopropane and the term electronegativity and explain why the CBr bond is polar. So I've pre-filled this. Electronegativity is the ability of an atom to attract an electron pair. I really do need to see that in a covalent bond. Okay, so they're the 2 things I really need to see in that definition. The explanation for this is bromine is more electronegative than carbon. So the Br is delta negatively charged and C is delta positively charged. And that would be your 3 marks. Okay, so it's wanting you to outline the mechanism for the reaction. Oops, there we go. Let's get that in focus. Outline the mechanism of the reaction of 2-bromopropane with an excess of ammonia. So this is going to be a substitution reaction. Ammonia has a lone pair of electrons and is nucleophilic. So we're going to get nucleophilic substitution. Okay, so I'm going to just set this up. Okay, so I've drawn the bromopropane out and here's the ammonia. So this is a polar bond. It's already given us, it's sort of setting this question up for us. So if we drew in the delta positive, delta negative, we can see the delta positive carbon there. This is a lone pair of electrons. That's going to be attracted to the carbon. And as the electrons are coming in, these electrons in the carbon-bromine bond are going to be repelled and bromine will take them. So what we form here is an ammonium ion. So we've donated this lone pair of electrons and that nitrogen becomes positively charged. The bromine's gone. We've still got the hydrogen in place. So we have this intermediate. And now what's going to happen is that this hydrogen, nitrogen-hydrogen bond, that electron is going to be given to nitrogen and we're going to lose this hydrogen. Now we can show that just as a straight hydrogen ion loss, or we can use a second molecule of ammonia and that ammonia will make a dative bond with that hydrogen ion or that hydrogen. The hydrogen this pair of electrons here will be given to nitrogen, and then what we form is our amine, NH2, CH3, CH3, and then we have this ammonium ion. Okay, so that would be the mechanism. And in terms of marks, you'd get 1 mark for this arrow, 1 mark for this arrow. So that's 1, 2. 1 mark for the intermediate is 3. And then 1 mark for the loss of this hydrogen ion here is 4. Okay, so this is a practical question, and reading through, we are distilling off cyclohexene. It was distilled off from the reaction. Complete the diagram, and the cyclohexane came off at 83. So we've got an open top here, so it needs to be closed off. We need to know the temperature as well, so we're going to put a thermometer in. So I'm going to draw in the thermometer, and the thermometer bottom is in line with the still head here, so it has to be somewhere in between that line, those lines. So if I drew the bottom in here, I'm going to get the marks. So, and this is, okay, so this, I'm going to label it just in case the examiner doesn't know. This is a thermometer. Now it's all right that, but it's still open. So I need to close off that end either with some sort of a bung or a stopper. So I've closed it off, and I'm just going to hash it so that it's obvious that it's closed off. Okay, so that's that end closed, and that's my thermometer, and I'm now missing a cooling jacket. So I'm going to put a cooling jacket on here. So this is water coming out. I'll go there, that'd be all right. And this is water that's going to come in. So if I do water out and water in, that looks perfectly acceptable to me. Okay, so 2 marks. So 2 marks was for this setup here, and then this setup here. Remember, you've got to have a clear route through the equipment from start to finish. If you close up any of those routes, then you would lose marks. Okay, so let's look at 3.2 then. The distillate was shaken with saturated sodium chloride solution. The cyclohexane was separated, and then it says state why cyclohexane was separated from the aqueous solution using the separating funnels. So that's a fairly straightforward because the liquids are immiscible. So liquids, the liquids are immiscible. Immiscible means cannot be separated. You could also write the liquids form 2 layers. That would be all right. Or you could say the liquids don't mix. So any of those which suggest that you've got 2 layers and they don't mix and they're immiscible. Okay, so to carry on with this procedure, the cyclohexane separated was as a cloudy liquid, and the student dried it, adding a few lumps of anhydrous, means there's no water there, anhydrous calcium chloride, and allowed the mixture to stand. So the reason we have this anhydrous calcium chloride is the calcium chloride itself is hygroscopic. That means it will pick up water. So what it's doing is picking up any stray water molecules in this cloudy liquid. So give one observation that the student made to confirm the cyclohexane was dry, then it wouldn't be cloudy anymore. So we could write that the liquid goes clear. So the liquid goes clear. or you could say not cloudy anymore. Okay. Right, so 3.4 is a calculation. So I'm going to quickly look at this, give you my thoughts, and then I'll work through it. So we added excess concentrated phosphoric acid to cyclohexanol. Now, we had a question earlier that had said, what's the process for making an alkene from an alcohol, and we had to use concentrated sulfuric acid or concentrated phosphoric acid. Well, if you'd not known that question and you'd read this, surely you would have seen that and then gone back to the other question. Anyway, so concentrated phosphoric acid. So we've got 14.4 grams of cyclohexanol. They've given us the formula mass. The student obtained 4.13 centimeters cubed of cyclohexane. Again, they've given us mass and they've given us density. So we're going to have to do some sort of density calculation. Calculate the percentage yield of cyclohexene obtained. Okay, so looking at this, I've got cyclohexanol. I always work with moles. So I think the thing I'm going to do here is I'm going to find out how many moles of cyclohexanol I've got. And if I can work out how many moles of cyclohexene I came up with, this is going to be a one-to-one reaction. So cyclohexanol to cyclohexene is going to be a one-to-one ratio. So if I know how many moles of cyclohexene I've got, that would be the amount I've produced, and I should have produced the total number of moles that would equate to cyclohexanol. So I could do what I got divided by what I should have got times 100, working in moles. How do I work out the mass of cyclohexene? Well, I've got the density of cyclohexene here. So density is mass divided by volume. So if I want the mass, it's going to be density times volume. So density is 0.810. The volume, this is in grams per centimeters cubed, it's given me centimeters cubed, so it's 4.15, and that would give me the mass of cyclohexene. I'll work that out and then I'll show you how I've done it here. Okay, so I've worked out the mass of cyclohexene, and I'll use that here, but I'm going to work down here. So moles of cyclohexanol as well. I've just done this. This is cyclohexanol to cyclohexene. It's a ratio of 1-to-1. So the mass of cyclohexanol was given as 14.4. So 14.4 grams divided by 100 equals, I'm going to do it on my calculator, 14.4 divided by 100 equals 0.144 moles. And I'm going to keep it in this format so that actually the examiner can mark it quite straightforwardly. Okay, so moles of cyclohexene, well, I've worked out that the grams I got were 3.3615, so 3.3615 grams divided by the molecular mass is 82. So I'm going to do that on my calculator as well. Let's do that. So 3.3615 divided by 82 is 0.04. I'm going to stay with 0.9939. I'm going to keep it long. I'm not going to shorten it just yet. Okay, so that's the amount I got. That's the amount I should have got. So the percentage yield, is what I got, which is 0.049939 over what I should have got, which is 0.144 times by 100, which equals, so divided by 0.144 equals times 100 is, so 28.46798, it says 46 798. So I'm going to stay with 3 significant figures. So 28 points, and I'm going to round this up 5%. 28.5%. Okay, so let's look at question 4.1. It gives us this compound here. It really doesn't matter what name it is, but they've told us it's prilocaine. It's an anaesthetic used in dentistry. That's the background bump of it. It just wants us to look at where the chiral centres are and draw a circle around the chiral centre. So a chiral centre is a carbon that contains 4 different groups. So looking here, the chiral centre, well, that's got 3 hydrogens, so it's not that one. That's got 2 hydrogens and 2 other. That's not that one. That one's got 2. That's not that one. It's not the N. What about this one? That's a carbon. It contains a carbon double bond oxygen. It contains a nitrogen. It contains a hydrogen. It contains a CH3. Yep. So this would be my chiral centre. So draw a circle around any chiral centre. So certainly that one. Let me have a look. Well, it's not this one. It's not that. It's not any of those. And that's got 3 hydrogens on. So that is the only chiral centre. And it's 1 mark. So I would say it's obvious that there's only one. Identify the functional groups in the prilocaine molecule. Okay, well, this looks suspiciously like an amide. I looked at it first and thought, oh, it's an amine. A tertiary amine, but because it's attached to this C double bond O, that makes this an amide linkage. And do we have an amide linkage? We do, so I'm going to tick that. So this is the amide, so that's the amide. There's an NH here, nothing else. It's so that's definitely an amine. So we've got an amine. Do I have any esters in here? C double bond O. No, don't have one of those. Ketone, well, I could have been sucked into thinking that this was a ketone, but because it's part of the amide, it's definitely not a ketone. And they didn't have anything for aromatic groups. So there we go. There's only those 2 from the choices they've given us. And then prilocaine is completely hydrolyzed in the human body to give a mixture of products. Okay, so it's completely hydrolyzed, and we've got 2 organic products from the hydrolysis. So let's go back here, and this is testing something called retrosynthesis, which means going back from making this molecule. What did we start with? We could have started with some sort of bromine compound and done a substitution reaction somewhere around here, but that's not going to lead to hydrolysis. Looking around this amide place, yeah, I could see that we could probably break it across this bond here, and we'd make an amine and some sort of carboxylic acid, or maybe some sort of acyl chloride, because the acyl chloride would certainly react with that amine there. So my 2 products then, but because it's hydrolyzed, so I can break it across there. So I'd be adding the elements of water. So if I drew out this aromatic ring with the N and the H, I know it's going to break there, and C double bond O, and then everything else that's on here, CH3, NH, and CH2, CH2, CH3. Okay, because it's hydrolyzed, I'm adding the elements of water, H, OH. So the water would break here, and I'd get a H plus, or a hydrogen and an OH. So where's that going to go? More than likely that would be my starting material, and that would be an OH. So this is a carboxylic acid and an amine. So I've added the elements of water across this amide bond. The hydrogen's gone to the nitrogen, and the OH has gone to the carboxylic acid. So as I say, I'm left with this amine and this carboxylic acid. Okay, so we're on to the next one. So we've got two optical isomers, and there's the chiral centers, F and G. F is the active compound in the medicine ibuprofen, and in the manufacture, both isomers F and G are formed. An enzyme is then used to bind to isomer G and catalyze its hydrolysis. After the products of hydrolysis of G, after the products of hydrolysis of G are removed, a pure sample of isomer F is collected. So what is it saying? So we've got these two isomers, and an enzyme is going to bind to this, hydrolyze it and remove it. So we're left with this, only this one isomer. So explain how a structural feature of the enzyme enables it to catalyze the hydrolysis. So thinking back to your lock and key mechanisms when you were teaching, learning biology, then it has to do with the shape of the enzyme. The enzyme has a specific shape, and it will only accept a specific spatial arrangement, so a spatial shape of these isomers. So what we can say is the enzyme has an active site. Okay. Isomer G has the correct stereochemistry. To bind. You could say that it has, you could say isomer G has it is a complementary shape as well. So isomer G is a complementary shape rather than complementary shape. Complementary is when you're saying you look lovely, whereas complementary means it completes the shape. Okay, how many marks is that? That's 2 marks. Okay, so I think we've answered that question. All right, so enzyme G has an active site, 1 mark, and isomer G has the correct stereochemistry to bind with it. Okay, so we're on to the next part of this question, where we've got a strand of DNA, the double helix. I apologise if you can't see very clearly these single and double bonds. I'm not sure what's happening with my camera. Okay, it says draw all the hydrogen bonds between the complementary strands in figure 3. So we need to be looking for hydrogen bonds. That's what we're looking for. And just seeing what I've got here, well, there's an oxygen and there's a hydrogen. I'll colour them in red actually. So that would be, we'd get a hydrogen bond occurring there, and we'd get a hydrogen bond occurring there. And normally we'd have more hydrogen bonds. Let's see what's close to each other. So that's one complementary strand, and here's another complementary strand. So let's see the hydrogen bonds. They've lined them up quite nicely for us. Okay, there's another one, and there's another one. Okay, so we've got 3 hydrogen bonds in this one and 2 hydrogen bonds in that one. Perfect. All right, so question 2. What is it? Question 2. Draw a, well, it's this next one. Draw a ring around each of the component parts that make up the cytosine nucleotide. So we have to recognize the cytosine nucleotide. Okay, so let me do that for you. Okay, so it asked for the let's see, draw a ring around each of the component parts that make up the cytosine nucleotide. So it's this part here. And this part here. And which phosphate group are you going to take? Okay, we can see that phosphate going up, that phosphate connecting. This is coming from a different molecule. It is actually this phosphate group. And can you see I've drawn the oxygen attached to the sugar here. So it's going to be this group there. Okay, so that is the second part. So draw the hydrogen bonds between the complementary strands shown as dotted lines. We've done that. You don't need to show the charges. Draw a ring around the component parts of the cytosine nucleotide, which we've done. State the meaning of the term complementary when it is used to refer to DNA strands. Okay, so complementary means they have base sequences that match, or they have nucleotides that match. So the base pairs match, e.g. We've got A to T and C to G. Okay, the base pairs match. So the term complementary, it's the base pairs are matching. Okay, so we're looking at this next one with the Kekule structure for benzene and the current structure of benzene. And we're looking at an enthalpy diagram of this. So we can see the relative stabilities. So basically, this representation of benzene is a more stable form. It takes a lot more energy to break these bonds, whereas this is less stable. It's higher in energy. It doesn't take as much energy to break those bonds. Okay, so the question has asked us, I'm just going to turn over now, to use this data to calculate delta H2. Okay, so we've got to calculate delta H2. So I'm going to input this data on the diagram, and I'll talk you through that once I've done it. Okay, so what I'm doing, I'm looking at atomizing or breaking all of these bonds apart to make 6 carbon atoms and 6 hydrogen atoms. So to do that, I have 3 CC bonds that I need to break, 3 C double bond Cs that I have to break, and 6 CH bonds that I have to break. And these figures are taken from this table over here. So 3 times 3, 4, 8, 3 times 6, 1, 2, and 6 times 4, 1, 2. I'll put those values in a minute. Now this side, this was a bit tricky because I trying to work this out, but I think I've got it. We can see that we're going from carbon solid to carbon gas. So actually what we're doing, we're atomizing the carbons here, and the clue for that is at this point here. So I'm atomizing it, but I'm atomizing 6 of them. So 6 atomizations of carbon here. So 6 times 715. And then I'm atomizing these hydrogen molecules into hydrogen atoms. And they are atomization. I'm not breaking the bonds because the bond enthalpy is for breaking 1 mole of 1 mole of bonds. The atomization enthalpy is to make 1 mole of atoms, okay? And well, actually what I'm doing here, I'm making 6 moles of atoms. So 6 times 218. Okay, I'm going to add those, calculate those two out and find the total. So I'm going to put a total energy here and a total energy here. And then I'll show you how we use this cycle to find out delta H2. Okay, so what I've got here is 5355 for this enthalpy here. And for this enthalpy here, I've got 5598. Okay, so I want to calculate H2. Just remember, depending on which way round the Hess cycle you go, wherever you start, wherever you finish, then it's the same whichever way round you go. So if I start, let's see, if I start at this position here, I'm going to start here. And I'm going to go up there and I'm going to come down here. So the height of this is equal to the height of this. Is that what I wanted to do? Works out, that would give me the answer. Or I could say, so I could say the height of this equals the height of this, and then it would be 5355 plus delta H2 plus 83 equals 5598, and I can rearrange the equation. Okay, or I could say if I start here and I go to here, delta H2 equals, and then it would be plus 5355 take away 5598 plus 83. Yep, so I'm going with the arrow, would equal this. Okay. So it depends which way around you go. So this equals, actually, if this equals, that would be the way around I go, isn't it? So I go from here and I go around this way and I'll come back to here. Okay, just as I was working this out, I realised I didn't add this up right. This is 5352. Okay, so if I want to do this, I'm going to this point here. I would come this way round. The cycle to this position here. So I can write this equation as delta H2 equals, and I'm going against this arrow, so it's minus 83. I'm going with that arrow, so it's plus 5598. I'm going against this arrow, so it's minus 5352, and I'm back to this position here. So when I add them up, it's plus 163 kilojoules mole to the minus 1. Okay, so I want to find this height here, this delta H here. So I'm starting at this position and ending in here. So I'm going to go around the cycle this way to get to the same position, and I've done the calculations that you've shown there. If you're not happy with that, just remember the two heights of these are exactly the same. So the total, when we add these together, equals this total. And you can just rearrange your equation and you'll find you'll still get plus 163. Okay, so I'm going to transpose that figure that I had here to here. Just make sure I put the right number in, which is plus 163 kilojoules per mole. Explain why the bonding in this is more thermodynamically stable than this. Well, this has got delocalized pi electrons. So delocalized pi bonds electrons, actually delocalized pi electrons in, there you go, make it more stable, just to finish the phrase off, make it more thermodynamically stable. Okay, there we go. And that's the answer to that question. Okay, so let's have a look at this. A mixture of concentrated nitric and concentrated sulfuric reacts with benzene. This is an incomplete mechanism for the reaction. Name the mechanism, complete it by adding any lone pairs of electrons involved in each step. So we better put lone pairs in. 2 curly arrows in step 1, so I need 2 curly arrows there. Curly arrow here and here and here. Okay, so lone pairs, let's put some lone pairs in. What's happening at this point? So this is what we start with, this is what we get. I can see that the NO, this has gained a hydrogen off here. So let's put the lone pair on there. There must be 2 lone pairs on that oxygen. I'm going to put 2 lone pairs on it. I can see that it's donated that electron to that hydrogen. This has received an electron, so we've split that bond, so that must have gone there. Do be very accurate with your arrows. Okay, let's have a look at step 2. So step 2's got this positive charge on it, and I can see that I've lost water, so I must have broken this bond here. So this is positively charged, so this must have lost its electron. So remember, there's 2 electrons in this bond, 1 donated by nitrogen, 1 donated by oxygen. The oxygen has taken both electrons, so nitrogen is without, that's why it's become positively charged. So that must have gone onto the oxygen, and oxygen no longer has a charge, and that's water, and we've got N2O positively charged. Perfect. Okay, and that's we've got the lone pairs and 2 curly arrows. We've got on step 1, we've got the curly arrow in step 2. Let's have a look at step 3. Okay, so I can see that this has added on to this. Look, there it is. And we've disrupted that pi bonding that's in here. And it's added at that point there. So, and that is missing an electron because it's positively charged. So the electron's gone from here then onto that nitrogen. Okay, and here it is, and that's disrupted, and there was only 1 curly arrow at step 3. We've got 1 curly arrow at step 4. So step 4, we can see we've reformed this benzene system here, these pi bonds, and we've lost the hydrogen. So this hydrogen's lost, so that will have lost, okay, that electron back to this system. Now, I've been very careful where I've put that arrowhead. I've put it quite close to this carbon here, because it is this carbon that is donated, that has that pi bond, makes up that pi bond. So do be careful. Don't put this this arrowhead right here where this positive charge is, because that's not right and you'll get penalized for that. So put it in the vicinity of this carbon as if it were making that ring. So if you were to draw that ring in, that arrowhead actually touches where the ring would be. Okay, and that is the mechanism for that one. So we can tick that off. Oh, I didn't name the mechanism. So the mechanism is electrophilic substitution. Electrophilic substitution. Okay, so basically we're substituting a hydrogen with an NO2 group, It's electrophilic because the species NO2 plus likes negative charged areas. So it's negative charge loving, if you like, or electron loving. That's what the philic means, loving. So it likes those negative charges. Okay, that's that one done. Let's have a look at the next one. So 6.1 is about equilibrium. Okay, so we've got 1 mole of diester with this molecular formula, and 1 mole of, it's added to 1 mole of water with a bit of the catalyst. So we can see here that we are breaking it down to 2 ethanoic acid molecules and this diol here. So we've got this molecule, which is some sort of diester. So at equilibrium, X moles of ethanoic acid are present in the mixture. So here's the acid X. So deduce in terms of X what's left. So we know that if we've got 2 moles of ethanoic acid, we're going to get 1 mole of this diol. So whatever the value of the ethanoic acid is, half as much is going to be the diol. So this is going to be X over 2. Okay, and we know that for every 2 molecules of water, we're going to get 2 molecules of this acid. So we're going to use as many molecules of water as we get acid. So this is going to be 1 minus X. And then we can see that for every 1 molecule of this compound, we're going to get twice as much of the acid. So for every 1 molecule of this, we're going to get 1 molecule of the diol. So we know we're going to get X over 2 amount of diol. So we must have used X over 2 amount of this. So this would be 1 minus X over 2. Okay, so that's our mixture in terms of X. Then deduce the structure of the diester. So let's draw, so let's draw this diol out. So we've got CH2, CH2, CH2. That'll have an OH on it. That will have an OH on it, but that's going to form the ester. So then that will form an ester with the acid, and there's the ester linkage, and then that will form the ester with the acid. Okay, so looks something like that. Did it say skeletal formula? Did it want skeletal formula? It's given it in in the mark scheme. It's given it in skeletal formula. So I'll just draw it as a skeletal formula. So that's 1, 2, 3. That's that. 1, 2, 3. So 1, 2, 3, and then that's going to be the oxygen. That's going to be the CH3. Oops. It's skeletal. That'll be there. Okay. Not great, but correct. Okay, so we've got a new equilibrium mixture, and it's given us the moles at equilibrium. It's wanting us to calculate how much water we've got, and it's given us the Kc value. Okay, so where I start from here is writing out the Kc equation. So based on this equilibrium here, so I'll write out the KC equation. Then I can either rearrange so that water's a subject of the equation and substitute, or I can substitute and then rearrange. Okay, I decided to write the KC equation out. So based on the products over the reactants, here are my values. So the acid squared and the diol to the power 1, water squared, and then this diester to the power 1. I've rearranged for the water. So water is H squared. It stays as it is. The KC just drops to the bottom here. Literally these two are just exchanging places. Now what I'm going to do is I'm going to substitute the numbers in, and I'm going to work out the value. Then I'm going to take the square root so that I get the concentration of water. Okay, so I've substituted the values in and I've worked it out. So this is the value of the water squared. Now, something I need to point out, there was no volumes given. So we're wanting concentration here. So concentration is the number of moles divided by the volume, and we were given no volume. Now in this, it doesn't matter. And the reason is because the total number of terms on the top equals the total number of terms on the bottom. So we've got 1, 2, 3 terms on the top, 1, 2, 3 terms on the bottom. So volume in this instance would cancel out. But if we'd got, say, only 2 terms on the top and 3 terms on the bottom, we would need that volume in order to work out concentration. Okay, so I'm just going to work this out. So the concentration of water is the square root of 0.35677, and there's my square root, and it's 0.35677 equals 0.597. I'm going to stay with 3 decimal places, and I'm just going to round. I don't have to round it up because it's 73, so 0.597.